Crude oil doesn't look very impressive. It's thick, dark, and smells like something you probably wouldn't want anywhere near your clothes. And yet, this sticky liquid powers cars, fuels airplanes, heats homes, and even helps make the plastic in your phone case. But here's the thing. Crude oil in its natural form isn't very useful. You can't pour it straight into a car or turn it directly into a plastic bottle. It has to be transformed. So today, we're breaking down how crude oil refining actually works, how that raw underground mixture becomes gasoline, diesel, jet fuel, asphalt, and so much more. Right here on History of Simple Things. Oil refining didn't start with massive industrial complexes. It began with a simple goal: making better lamp fuel. In 1859, Edwin Drake drilled the first successful commercial oil well in Titusville. At the time, the main product people wanted was kerosene for lamps. Crude oil was heated in basic stills to separate out kerosene, while much of the rest was discarded. Then came the automobile boom in the early 20th century. When Henry Ford introduced the Ford Model T, gasoline demand skyrocketed. Suddenly, refiners needed smarter, more efficient ways to turn crude oil into large amounts of fuel. That's when refining technology rapidly evolved into the complex, highly engineered process we see today. Crude oil isn't one substance. It's a mixture of hundreds of different hydrocarbons, molecules made mostly of hydrogen and carbon. These molecules vary in size. Some are light and evaporate easily. Others are heavy and thick. The first major step in refining is called fractional distillation. Inside a refinery, crude oil is heated to around 350–400 degrees Celsius in a furnace. This turns most of it into vapor. That vapor then enters a tall structure called a distillation column, which can be over 30 meters high. Here's where physics does the work. Different hydrocarbons have different boiling points. Lighter molecules, like those used in LPG and gasoline, boil at lower temperatures. Heavier ones, like diesel and lubricating oils, boil at higher temperatures. As vapor rises inside the column, it cools. The heavier molecules condense lower down. Lighter molecules travel higher before condensing. Each level of the tower collects a different fraction. From top to bottom, the column typically separates refinery gases like propane and butane, gasoline, naphtha, kerosene used for jet fuel, diesel, heavy gas oil, and residue used for asphalt or further processing. At this stage, the oil has been separated but not fully upgraded. Here's the challenge. Crude oil naturally contains a lot of heavy hydrocarbons, but modern society needs more gasoline and lighter fuels. So refiners crack the heavy molecules. Cracking is exactly what it sounds like, breaking large hydrocarbon molecules into smaller ones. This is done using high temperatures, pressure, and often catalysts. One of the most important processes is fluid catalytic cracking, FCC. In this method, heavy gas oil is exposed to a fine catalyst powder at high temperature. The catalyst speeds up chemical reactions that split long hydrocarbon chains into shorter ones, producing more gasoline and other valuable fuels. There's also hydrocracking, which adds hydrogen under high pressure. This not only breaks molecules apart, but also improves fuel quality by reducing sulfur and impurities. Without cracking, we simply wouldn't have enough gasoline to meet global demand. Some fractions like naphtha aren't very useful on their own. They need to be chemically rearranged. That's where catalytic reforming comes in. Instead of breaking molecules apart, reforming reshapes them. Straight-chain hydrocarbons are converted into ring-shaped or branched molecules. Why? Because these structures burn more smoothly in engines. This process increases a fuel's octane rating, its resistance to knocking in engines. High-octane fuel allows modern engines to run efficiently and safely. Reforming also produces hydrogen as a byproduct, which is later used in desulfurization processes. Crude oil naturally contains sulfur and other impurities. When burned, sulfur forms sulfur dioxide, a major air pollutant that contributes to acid rain. So before fuels are shipped out, they must be cleaned. In hydrotreating units, hydrogen is used to react with sulfur compounds. The sulfur is converted into hydrogen sulfide gas, which is then removed and processed separately. Modern environmental regulations require ultra-low sulfur fuels. For example, many countries now limit sulfur in diesel to 10 to 15 parts per million. Refineries are designed to meet these strict standards. This cleaning stage is critical, not just for engines, but for air quality. Even after all these processes, refinery products aren't finished. Gasoline, for example, isn't just one stream from the distillation column. It's a carefully blended mixture of different components: cracked gasoline, reformed gasoline, alkylate, and additives. Refiners adjust blends depending on climate, regulations, and performance needs. For example, fuel formulas differ between summer and winter to control evaporation rates. Diesel, jet fuel, and other products are also blended to meet precise specifications. Think of it like cooking. Distillation gives you ingredients. Cracking and reforming modify them. Blending creates the final recipe. Not everything becomes fuel. The heaviest residue from the distillation column can be processed further in units like coking, which converts it into lighter products and petroleum coke. What remains may become asphalt for roads or feedstock for industrial materials. Nothing is wasted if it can be transformed into something useful. Modern refineries are massive, complex systems operating 24/7. They integrate chemistry, physics, thermodynamics, and engineering at enormous scales. A large refinery can process hundreds of thousands of barrels of crude oil per day. And yet, the core idea is surprisingly simple. Separate what's there, break what's too big, rearrange what's inefficient, clean it up, and blend it properly. That's how a thick, underground mixture formed from ancient organic matter over millions of years becomes the fuel in your car, the jet fuel in airplanes, the asphalt on highways, and the raw material for plastics. Crude oil refining isn't just about making gasoline. It's about transforming complexity into utility, turning raw nature into the structured energy system that powers modern life. And all of it starts with heating a dark liquid and letting chemistry do the rest. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution.